Welcome to the last session in electrochemistry. In this session, I will be discussing the chemistry of corrosion, and that being a very brief topic, I would follow it with a set of revision questions and problems for your benefit. Now when we say corrosion, you think of always only rusting of iron. But not only iron, but other metals like copper, aluminium, tin and zinc also corrode. But why is corrosion so relevant only to iron? Is because the rust that is formed on the surface of the iron peels off. When you touch rust, it comes off with your hand and it exposes fresh layers of the metal. So corrosion penetrates deep inside and after some time the entire metal is lost. Corrosion always causes a huge loss of materials and money. To prevent corrosion, so naturally we have to understand the chemistry of corrosion. Corrosion, involves slow oxidation of metals. But if we have to define corrosion properly, we can say it is the loss of useful metals as their compounds. Where we want to use the metal as it is seen in the picture, it's of no use if it is converted to the compound, isn't it? Compound form, isn't it? So far you have been looking at corrosion only from the commonest point of view as the loss of metal. Now we are going to look at it from the chemist's point of view. In the presence of air and moisture, iron corrodes. What happens is, on the surface of the iron, a few iron atoms lose electrons and get oxidized to Fe2+. These electrons move along the surface of the metal, and in the presence of oxygen of the air, the hydrogen ions take these electrons. They take up these electrons to form water. So how many electrons you need? 4 electrons. Form water. Where do you get these hydrogen ions from? In the atmosphere, you have carbon dioxide in the air and moisture also. So these two react to form carbonic acid, which makes these hydrogen ions available. So the iron losing electrons forms the anode, and that has an electrode potential of 0.44 volt. 44 volt. The second reaction is the reduction part of it, which has an electrode potential of 1.23 volt. Does it form an electrochemical cell? If this is the oxidation part and this is the reduction part of it, do they together form an electrochemical cell? For that we have to calculate E0 cell. E0 cell is E0 reduction minus E0 oxidation, isn't it? So it is 1.23 minus 0.44. This is positive. Hence, an electrochemical cell is set up on the surface of the iron and the reactions are spontaneous. They continue further. The overall reaction can be written as Fe solid plus O2 gas plus 4H plus aqueous giving 2Fe 2 plus aqueous plus 2H2O liquid. This is the overall reaction taking place, and so many miniature electrochemical cells are set up on the surface of the iron. Not only that, the Fe2 plus that is formed is further oxidized to Fe3 plus. This equation shows you the oxidation of Fe2 plus to Fe3 plus and formation of ferric oxide. You see hydrogen ions also are released in this equation, which keep the corrosion process going on. This Fe2O3 exists as the hydrated ferric oxide, the form of Fe2O3 XH2O, which we call rust. This is about the chemistry of rusting of iron. Other metals like zinc, tin and aluminium also form their oxides, and if you have seen the copper metals, copper vessels and all, they are coated with a green layer, isn't it? That is the CuOH twice dot CuCO3. That is the green layer that you find on the copper vessels. But in these cases, the case of these metals, the whatever compound is formed completely coats the metal and acts as a preventive layer. So corrosion stops almost with the topmost layer, and the metal is saved from complete corrosion and complete loss of metal. Once we have understood the chemistry of rusting of iron, let us see how these methods of prevention that we apply normally are helpful in preventing corrosion. The simple methods are, we can say, applying of oil, then painting, we do painting of the iron objects. Thirdly, we can say coating of metals like zinc and tin. In the case of coating of zinc, it is called galvanization. You can use tin also for coating. And finally, we can say the sacrificial anode. In the case of the first three methods, we are cutting off the supply of oxygen. We cut off the contact between the metal surface and the atmosphere. So that helps in preventing of corrosion. In the case of coating of metals like zinc and tin, these metals can be oxidized. But as I just now told you, the oxide layer completely coats the metal and prevents it from further corrosion. These are simple ones. In the case of the last one, sacrificial anode, what we do is, in the case of large iron pillars supporting bridges and all, to prevent the corrosion is of very high consequence, isn't it? So highly reactive metals like magnesium or a zinc bar is connected to the iron pillar by means of a wire, and these are buried in the soil very close to the pillar. So when a more reactive metal is connected to this iron cannot form the anode. It cannot lose electrons and form anode. It will be the more reactive metal which will be readily losing the electrons and forming the anode. So that metal, whether it is zinc or magnesium, that will form the anode. The iron of the pillar forms the cathode. So there is no loss of iron as ions there. After some time, this anode will be completely lost. It will be converted into the ion and will be lost as a compound. So that has to be replaced. In this case, we can say we can also call it cathodic protection. It is the iron forms the cathode. So it is called the cathodic protection, or it is the sacrificial anode. So this is about understanding of corrosion as an electrochemical phenomena. The question could be just explain corrosion as an electrochemical phenomena. That is how it is asked. So you have to write the equations which form the anode and cathode in the case of the corrosion of iron, and the overall equation you have to write and say, give the E0 cell value and say how E0 cell is positive and the reactions are spontaneous. Also there is a reasoning question as to why rusting is so relevant particularly to iron. Now I will be following this with an assignment of questions and problems. In this assignment I have given you a few questions and problems. Answering these questions and problems will give you a deep insight into the concepts that you have learnt in the lesson. To derive the maximum benefit, go through the questions, pause, write the answers in a paper, and then listen to the discussion of the answers. To begin with, I have given you 3 questions followed by the discussion of answers to these 3 questions. In the first question, you are asked to give the sign of del G for an electrolytic reaction and electrochemical reaction. You know that in an electrolytic reaction, we have to pass electricity to bring about a chemical reaction. So, is it spontaneous or not? It is not spontaneous. So, del G is positive because it is non-spontaneous. It is positive for electrolytic reaction. In an electrochemical reaction, we perform a spontaneous reaction and produce electricity. Hence, delta G is negative. Electrochemical reaction. Second question asks you to evaluate the mass of an element of atomic mass atomic mass X, which will be deposited on passing 1 coulomb of charge. So, atomic mass is X. Now, you know that to deposit 1 gram atom of any element, you have to pass NF coulombs of charge, where N is the charge on the ion. Now, this is said to be a monovalent metal. Hence, when you pass 96,500 coulombs, that is 1 Faraday current, you will be depositing 1 gram atom of the element, that is X grams. So, when you pass 1 coulomb of charge, it will be X by 96,500 grams. It is as simple as that. In the third question, first subdivision, you have 0.1 molar HCl and 1 molar HCl. You are given these 2 solutions. You are asked to find out which one will have higher conductivity. You know conductivity depends on concentration. Since the second solution is of higher concentration, this will have higher conductivity. And in the second subdivision, you are given a 0.1 molar KCl at 25 degrees Celsius and solution of same concentration 0.1 molar KCl at 50 degrees Celsius. Here the concentrations are same, but the temperatures vary. The one at higher temperature will have greater mobilities for the ions. So, when the solution is at higher temperature, the ions also will have higher mobilities. Hence, conductivity will be more. So, in this case also, the second one will have higher conductivity. In the third pair, you are given 0.1 molar HCl and 0.1 molar NaCl, both at 25 degrees Celsius. Here concentrations are same and temperature also is the same. So, what should we compare here? In the first solution, here you have H plus ions and Cl minus ions. In the second solution, you have Na plus ions and Cl minus ions. So, that point of comparison should be only the size of the ion. Na plus being a larger ion should have lower or higher mobility. A larger ion will have lower mobility. Hence, the first solution will have higher mobility and higher conductivity in this case. I suppose it is clear. Now, you can pass on to the next set of questions. Try to answer these 3 questions and then listen to the discussion that follows. In the fourth question, you are asked to find out 1 Siemens meter square mole inverse is equal to how many Siemens centimeter square mole inverse. I want to tell you that there is no need to remember the relationships between these units. You can derive them easily, as I will show here now. 1 Siemens meter square mole inverse is equal to, you can write for meter square 100 centimeter the whole square mole inverse. So it is 10 to the power 4 Siemens centimeter square mole inverse. The second one is, you are asked to find out 1 Siemens centimeter inverse is equal to how many Siemens meter inverse. I will write this as 1 Siemens centimeter square centimeter inverse is equal to Siemens by centimeter, isn't it? So we can write it as Siemens by 10 to the power minus 2 meter. So it becomes 100 Siemens meter inverse. That's all it is, very simple. Then in the fifth question, you are given 3 important values that you come across in electrochemistry. One is this is K. This is K here. It's E naught cell, and this is del G. Equation 1, equation 2 and equation 3. You are given equation 1 as del G is equal to minus NF E naught cell. You are asked to write other two relationship. This is only to recall the 3 important mathematical relationships which will be useful in working out problems in this unit. What is the relationship between E naught cell and K? E naught cell is equal to 2.303 RT by NF log K, and the relationship between K and del G is equal to minus 2.303 RT log K. So when it is represented this way, you will easily remember the relationship between the 3 values K, E naught cell and del G. In the sixth question, you are given 2 solutions. 1 mole of KCl dissolved in 250 ml water, and then another solution in which 1 mole of KCl dissolved in 500 centimeter cube of water. You are asked to find out which one will have a higher value for its K and which one will have higher value for molar conductivity, lambda m. Here 1 mole is dissolved in 250 ml and here 1 mole dissolved in 500 ml. This is more dilute. So the one which is more concentrated will have greater number of ions per unit volume and hence will have higher conductivity. So if you say the kappa value of first one is Ka will be greater than Kb. This is a very simple one. And secondly, to compare their lambda m values, we will use the relationship lambda m is equal to kappa into volume V, where V is the volume containing 1 mole of the electrolyte. In the first case, for the first one we will write lambda m is equal to Ka into 250 because it is 250 centimeter cube of solution. Now for the second one, lambda m is equal to Kb into 500 centimeter cube of solution. You know Kb is lower than Ka, isn't it? Kb is less, but the volume is 500 here, which more than compensates for the decrease in the value of K. The net result is the second one will be higher. This one will be higher. Though Kb is less than Ka, the volume is so much higher than in the previous one that these two together will have a net higher value than for the solution A. So for solution A will have a higher conductivity, but lambda m of B is higher. Is that clear? So we will pass on to the next section of the assignment. In this question, you are given a few pairs of ions and you are asked to find out if a reaction between the given pair is feasible using their electrode potentials. I will solve the first one for you. The ions given in the first pair are Fe3 plus aqueous and I minus. Fe3 plus aqueous reacts with I minus. Supposing it were to react with I minus aqueous, what could be the reaction? Fe3 plus can only undergo reduction, so it can become Fe2 plus aqueous, and I minus can lose the electron to become half I2. From this we find that Fe3 plus, since that undergoes reduction, that should be the cathode, and I minus undergoes oxidation, so it should be the anode. So we can calculate E naught cell is equal to E naught cathode minus E naught anode, that is 0.77 volt minus 0.54 volt. This is positive, hence we say the reaction is feasible. I suppose it is clear to you. So in the same way, for each given pair of species, you have to write the equation, a possible equation, which will help you to find out which should form the anode and which one should form the cathode. Calculate E naught cell, and using the sign of the E naught cell, you can predict whether the reaction is feasible or not. To continue with the solution, in the second pair, you have the species Ag plus aqueous and Cu solid. Ag plus can only take up an electron and form Ag solid, and Cu can lose electrons to form Cu2 plus aqueous. Obviously, Cu is the anode because it is undergoing oxidation, and Ag plus is the cathode because it is forming the undergoing reduction. So E naught cell is equal to 0.80 volt, that of silver electrode, minus 0.34 volt, that of copper electrode, which is positive. The reaction is feasible. Let us pass on to the third one, in which you have Fe3 plus and Br minus. Br minus. Following the first example, you should be able to write the equation here. Fe3 plus becoming Fe2 plus aqueous, and Br minus becoming half Br2 liquid. So E naught cell is equal to, the reduction part is Fe3 plus becoming Fe2 plus, so that is 0.77 volt, and the anode has a potential of 1.09 volt, and E naught cell is negative. Reaction is not feasible. In the fourth one, we have to consider a reaction between Ag solid and Fe3 plus aqueous. Ag can become Ag plus aqueous by losing an electron, and Fe3 plus can gain that electron to form Fe2 plus aqueous. E naught cell is equal to 0. Which is a cathode here, it is iron, so it is 0.77 volt minus 0.80 volt, which is that of silver electrode, which is negative. Hence this reaction is not feasible. This is the fourth subdivision. The fifth subdivision has Br liquid, Br bromine liquid and Fe2 plus aqueous. There is no problem in completing the equation. 2 Br minus aqueous plus 2 Fe3 plus aqueous. So E naught cell is equal to E naught of cathode, which is the iron, 0.77 volt, and the anode has a potential of 1. Here we know Br2, which is becoming 2 Br minus, is the cathode, isn't it? So that is 1.09 volt minus 0.77 volt. So this is positive. The reaction is feasible. So you have learnt how to predict whether a reaction between the given pair of ions is feasible by considering their electrode potentials. The last three questions are problems. I have selected these problems which are at a slightly higher difficulty level than the ones I discussed in the sessions. Try to work out these problems by yourself and then check with the solution. In the 8th question, you are required to calculate E reduction of the chlorine electrode. The electrode is Pt bar Cl2 gas at 1.5 bar pressure bar Cl minus ion at 0.01 molar concentration. In such problems, whether it is required in the problem or not, it is advisable to write the equation for the cell reaction or electrode reaction. The electrode here reaction here would be Cl2 gas plus 2 electrons giving 2 Cl minus aqueous. To write the Nernst equation, E half Cl2 bar Cl minus is equal to E naught half Cl2 bar Cl minus 0.059 by 2 log concentration of the chloride ion to the power 2 by pressure of chlorine gas. Substituting the value for E naught and the concentration of Cl minus ion and the pressure of Cl2 gas, we would be writing it as 1.36 volt minus 0.059 by 2 log, this is 0.01 molar to the power 2 by 1.5 bar. To do the calculation without mistakes, you can follow the method I show you. You can change the sign here, 0.059 by 2 logarithm of 1.5 by 10 to the power minus 2 the whole squared. So this will become 0.0295 into, this will be logarithm of log of 1.5 into 10 to the power 4. So that would be easy for you to solve. So the final answer would be 1.483 volt. You can, I'll just show it, then brackets here. This part alone you can take and substitute the logarithm as it is here, and then when you work out you will get this value. In the 9th problem, you are asked to calculate DMF of the cell represented by bromine liquid bar Br minus at 0.01 molar, salt bridge H plus at 0.03 molar concentration, bar H2 gas at 1 atmosphere pressure, or PT. The equation for the cell reaction would be 2Br minus aqueous plus 2H plus aqueous giving Br2 liquid plus H2 gas. E0 cell for this is 0 for the hydrogen electrode minus 1.08 for the bromine electrode. So it has a negative value of minus 1.08. Now Nernst equation will be this way: E cell is equal to E0 cell minus 0.059 by 2 log concentration of the bromine liquid into pressure of hydrogen gas by concentration of Br minus ion to the power 2 and concentration of H plus ion to the power 2 as per the equation. That is why we say writing the equation will be a lot helpful. This is minus 1.08 minus 0.059 by 2 logarithm of, now bromine being a liquid, its concentration can be taken as unity. For hydrogen gas, we can substitute pressure in the place of concentration, and the pressure here is 1 atmosphere. So the numerator becomes 1. Both terms are unity. And in the denominator you have 0.01 square into 0.03 square. We can write it as 0.0295, and here I would do it this way: 10 to the power 4 into 10 to the power 4 by 9. This will give you a value of minus 1.08 minus 0.0295 into 7.0458. Remember, this is 10 to the power 4. I suppose it is clear to you. And you get a final answer of minus 1.288 volt. In the 10th problem, you are asked to calculate the EMF of a cell represented by the equation SN4 plus 1.5 molar plus zinc giving SN2 plus at 0.5 molar plus Zn2 plus at 2 molar. Let's write the Nernst equation. E cell is equal to E naught cell minus 0.059 by 2 log concentration of Sn2 plus into concentration of Zn2 plus by concentration of Sn4 plus. We are given the E naught value as 0.89 volt in the problem minus 0.059 by 2 log of, substitute the values of the concentration here, 0.5 into 2 by 1.5. So you can continue working out. This will be log of 1 by 1.5. So to make easy calculation, not by 9 by 2 log 1.5. I have changed the sign here, so I am writing it as log 1.5. So take the value of logarithm of 1.5 here and do the calculation. You will arrive at the final value of 0.8951 volt. I would like to extend the problem a little bit here. I am going to ask you, how will the E cell value will change? How will E cell change if concentration of Sn4 plus is increased? Sn4 plus is increased. Just think, see where the concentration of Sn4 plus occurs in the equation for the calculation. In this equation for the calculation of E cell, Sn4 plus occurs in the denominator of a term which is associated with a negative sign, isn't it? So you can easily see that when Sn4 plus concentration increases, the overall value should increase because the second term becomes smaller, so the overall value should increase. I suppose you are able to see that clearly. Instead of 1.5, if you have a higher value, say 2 or 2.5, whatever it is, the second term will reduce in value, and so there will be net increase in value. So when we increase the concentration of the Sn4 plus ion in the cell, the E cell value increases. That will be your answer. E cell increases. I suppose a discussion of all these questions and problems in the revision assignment would have helped you in understanding the concepts better. Thank you.